Artificial intelligence has a problem with generating stuff. It's really hard. Classification is trivial. Basically, everyone's first AI program was an MNIST classifier, but creating an algorithm can generate those same digits? Well, that requires exponentially more training time and data. That's just talking about images. Generating photorealistic video is at the forefront of current AI research and is still next to impossible to do on a home computer. Nevertheless, I wanted to see what I could do. So I created PongAI, a machine learning model that generates videos of the 1972 game Pong. PongAI is a machine learning model that's able to generate a fully interactable game of Pong. It works like this. The player provides the actions, telling PongAI what to do and where to move the paddle. PongAI does everything else. It handles the input management, calculates all of the physics interactions, and renders all of the individual frames, completely in real time. Let's take a look at how the code behind this model works. At a high level, it is split up into two neural networks, a renderer and an engine. The engine is a fully connected, recurrent model that uses long short-term memory layers to convert an action into a latent representation of the next predicted frame. The renderer is a convolutional autoencoder that takes the latent representation generated by the engine and transforms them into the full frames. It goes without saying that this isn't the best game of Pong ever made. Since the rendering is handled by an autoencoder, the straight lines that you normally find are much less well defined. There is also the occasional visual or physics glitch, such as the ball bouncing off of thin air, or being teleported to a different location. These issues are mainly caused by a run-on effect, where the renderer draws an artifact in a random location. Generally, these artifacts will be small enough that the next frame will simply discard them, but in a few cases, they can break the engine. Since this program is made of two distinct models, it's relatively simple to swap one of them out. Imagine an autoencoder that's been trained on a generalized dataset of all Atari games. Instead of needing to train the engine renderer pair on each game, you could train the renderer on all of the environments and then just create a specific engine for each game. This would drastically decrease training time, as in my experience, the renderer takes far longer to train than the engine. Despite not having many practical uses in its current form, this model could be expanded upon in a few interesting ways. Firstly, exploring the idea of training multiple engines with the same renderer could lead to interesting results. It might also be possible to use engines with a different renderer from the one that they were trained with. However, for this to work, the renderers would need to encode the frames in precisely the same manner. It's exciting to think that just a few years ago, making this on a home computer would have been next to impossible. What, then, might we be able to build in just a few years from now that currently seems so unlikely?